in what way is the DFT imperfect, okay? And along the way, what I will do is I will remind you of what the fudge are we trying to do with the DFT, okay? So first I'll start actually at the result. So we went through the derivation of the DFT, and then we ended up with these equations, okay? And the important thing to just emphasize is that with these equations, you have some time domain signal, Hn, okay, which has capital N points in it, okay? And what you do in the DFT is you give these points, this is point 0, point 1, point 2, up to point n minus 1. It's a list of numbers. You give it to the DFT, and out pops another list of n numbers. Actually, it's these numbers here. Tunk, 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 tunk. How do we get these numbers? We plug it into this equation. Okay, now my question is, can I calculate this equation on a computer? Yes or no? Like really in a very easy way. Yes. If there's integrals with df's and stuff here, then sometimes you can do it on a computer, but in general you can't. You have to have some closed form solution. The cool thing about the DFT is that we can calculate it on a computer, and it's actually pretty simple. Very quickly, import numpy, and then, okay, you can write the for loop, but you can also just do np.fft.fft. I will tell you later on why it's called FFT, but it calculates the DFT, the discrete Fourier transform. And then you just, I have no idea whether this will work. You give it a list of number, and then you run that cell. Okay, it says np not defined, import numpy as np. Okay, so if you're not an idiot, you get the signal out. Okay, and there's a list of, this is 1, 2, 3, 4 numbers. They're complex. Okay, freak out a little bit, but we've got the answer. But now the question is, wonderful, great, Herman. So you explained to us how to get a list of numbers if I give you some other list of numbers. The question is, what does this tell us? Okay, and what we hope is that the DFT tells us something about the spectrum of the signal that I fed in. Okay, and that's what we're trying to do. Okay, you guys with me? So now we go back to this pretty intense DFT slide, which you will definitely look at several times again. Let's just remind ourselves of what are we actually trying to do. Let's say someone sang a note, okay? And we want to know what is the spectral content of the note that he sang. We want to know, is it at the good frequency? Is it actually at the note C or something? So that we can evaluate whether he's a good singer or not. Okay, so in this room, there's a continuous signal coming from his mouth. The signal doesn't look like this, but let's just pretend for the second that this is what the signal looked like. It's a continuous signal, okay, a real world signal. For the moment, let's pretend that the spectrum of that signal is this green line. It's not. This is a made-up picture. But let's just for the moment pretend that it is. What I want from the DFT is I want a computer program that gives me samples of this spectrum. Okay? In other words, I want some algorithm in which I can feed it, ideally, the continuous signal that he's singing. And then what I want is I want that algorithm to give me discrete samples of that signal on a computer so that I can, process it in some way. So that's what we want from the DFT. In a perfect world, we want a sampled version of this thing so that I get a list of numbers that tells me about the spectral content of this continuous thing on a computer, and then I can check, does it match the frequency of a note C, yes or no? The DFT doesn't give this to me. It tries to approximate this. Okay, so just hold on to that. The DFT is going to try and approximate this. It's not going to do it perfectly. So how does it screw up? Aliasing. So the moment we're sampling the note that he's singing, the moment we do that, if that note is not band limited, we're going to get aliasing, okay? If he has this amazing ability to sing a perfect sinusoid, which actually doesn't sound great, we need some timbre from his voice, but if he had the ability to sing a perfect sinusoid and we sampled high enough, we wouldn't get aliasing, okay? And we would be happy. But in most real-world signals, we'll get aliasing, okay? So the DFT isn't perfect. I'm not getting this. I will sample this. Okay, but even that is not true. So the second way in which the DFT is not perfect, to evaluate his note that he's singing, I will have to record it until the end of time. We can't do that. So what we're going to do is we're going to take a window of the note that you're singing. We're going to say, okay, you've sung this for 6 seconds now, or 10 minutes, or whatever. Now we are ending. We can't sit here all day to evaluate the pureness of your voice. Okay, so we take a window. The moment we take a window, we're multiplying in the time domain. In the time domain, we're multiplying with the window. What happens in the frequency domain? We're convolving with a sync. Okay? There's maybe other windows that's nicer than a sync. Fine, we can deal with that. But we're going to convolve with something here. We're convolving with a sync. Multiply in the time domain with a window, convolve in the frequency domain with some sync-like function. What that does is it adds some ripple on my signal. Let's say you were able to produce a perfect sinusoid. Like actually a perfect sinusoid. This is a perfect sinusoid. Then what we would have done is, okay, we will sample it. Let's just pretend for the moment that we're sampling high enough so that we don't get aliasing. And then we would multiply this thing with a window. That means we're convolving with a sync-like function, which means in the frequency domain we get wobbliness, blobbiness. Okay. Now I will ask this question. Does the DFT give me like a sampled version of this thing? Yes or no? Yes or no? Yes. That is what the DFT gives me. It gives me exactly the heights of this wobbly thing. It gives me those heights exactly, but that's not what I actually wanted. Okay? What I actually wanted was these points. What I got is these points, but it gives me those points exactly. If this is a sinusoid and we take the DFT of this sinusoid, in other words, we sample causing aliasing if we don't sample fast enough, and then we window, what we will do is the DFT will actually give us the heights of those points. The way in which we get these sample points out is that we're going to take this thing and periodically repeat it, because that corresponds to convolution in the time domain, which is like multiplication in the frequency domain. So in order to get these points, we will get these points exactly. What we will do is we will take this thing and periodically extend it. Does that make sense? So I'm going one step further, and all of that is on this slide. So we periodically extend it, and that really just samples the wobbly points, but it samples them exactly. This was something that confused someone yesterday. The periodic extension thing, you do not have to do it in the computer. Okay? It's something that happens behind the scenes in the mathematics that then gives us this equation. On the computer, you don't have to give it this thing repeated until the end of time. All I have to do is I give it these samples, and in the back of my head, I just remember, okay, this thing is being periodically repeated in order to sample the spectrum, and that kind of happens in the mathematics and in the steps. But what I give it is I just give it these n samples. And what I get out is the heights of the wobbly signal. Okay, and these are these heights exactly. And these heights correspond exactly to the strengths of the frequencies at those points. Nod. I just want to check all my notes that I've said everything that I want to say. Okay, I've said everything that I want to say.